Good afternoon, everyone. My name is Cha Zhang. I'm a researcher at Microsoft Research. It's my great pleasure to introduce our next speaker, Dan Bohos. Dan is a PhD from Carnegie Mellon University in 2007, and he's currently a senior researcher at Microsoft Research in the Adaptive Systems and the Interaction Group. Dan is very famous at our research org because he built a lot of very fancy toys in Microsoft. If you go to our building 99, you want to enter the elevator. Before you press the button, the system will call the elevator for you, and that's Dan's work. And you walk out the elevator, you will see a robot in front of you, and you can ask directions, where's Dan's office is. So without further ado, let's have Dan talk about all the systems he built. Thanks.
All right. Thanks a lot for the introduction, and it's awesome to be here and give this talk. Thanks for the invitation. I guess I'm the guy that's sitting between you and dinner, so I'll try to make this lightweight and fun. There's going to be a bunch of videos. One thing that I would like is for you guys to ask questions anytime you feel like you want to know more about something. I'm not going to go into a lot of technical detail. What I want to do is give you sort of a high-level overview of this area of research that I've been spending time over the last 5-6 years. And it has to do with physically situated dialogue, with how do we do language interaction in physical settings, in open world settings. So I'm going to try to go through a couple of examples of research we've done over the years, show a bunch of videos, and then if there's time at the end of the talk, I'm going to try to highlight some of the important challenges, I think, and opportunities in building this kind of end-to-end integrative AI systems that leverage different kinds of technologies, from vision to speech to machine learning to everything together, to try to construct an experience where the system acts as more than the sum of its parts. Before I get going, I should also say that a lot of the work that we've been doing over the years involves contributions from many, many people. So while this is a research effort that primarily myself and Eric Horvitz are leading at MSR, there's a lot of contributions here from people across different areas, from fabulous interns we've had over the years, so I'd like to acknowledge all of them before going on. Okay, so I'm not going to see you guys. It's pretty bright out here, but if someone has questions, yell or raise a hand or something. I do want to make this interactive if possible. Physically situated dialogue. Well, let's start with dialogue. Dialogue, even if you look at it in its perhaps simplest form, which might be just text, it's a quite complicated problem. It's like almost AI complete. If you try to build a chatbot that does something reasonable, it's quite difficult. You have to solve, in general, when you deal with dialogue, a number of problems like natural language processing, parsing, things like reference resolution, coming up with representations for semantics, for discourse, figuring out how to do grounding, how to establish mutual ground in an interaction. There's lots of really interesting, fascinating problems people have worked over the years. Now, a lot of people are interested in adding speech to this. That brings us to spoken dialogue. And the prototypical example here is these days, these mobile assistants that we have in our phones where you can kind of speak a query into it and hopefully get a good answer back. Adding speech into the mix brings up a number of other problems, right? You have to deal with speech recognition and language understanding and speech synthesis and now all the errors that the speech recognizer might produce and so on. Now, in my work, I'm kind of trying to push this one step further and ask the question, what happens if I add information about the physical surrounding context? When we interact with language with each other, we're always situated, we're in space, we look at each other. And so what happens if we also not open up just the audio channel, but open up the vision channel and open up the eyes? And so in my work, I work with robots or with these virtual agents, and the goal is to think of building computational models that enable machines to engage in spoken language interaction in this kind of physically situated open world settings. And so the way we've gone about this over the years is by building systems. So we build a bunch of these systems and we deploy them in the building and we let people interact with them and we see what goes wrong. And then we try to fix it. That's how we discover sort of what are some of the core problems we have to solve to make this work for real. And over time, we've worked with systems based on avatars, where you can walk up to it and talk. And more lately, we started playing, as I mentioned, with robots. I'm going to show you 2 example videos of 2 of these systems, just to ground things and make everything kind of concrete, to give you a sense about the nature of the systems we're building. The first one is this virtual assistant that lives in front of Eric's office and kind of tries to do a little bit of a personal administrator job. It's not that good at it. But the system is connected to a large backend that has been developed through years of research at MSR, a large infrastructure that has predictive information about Eric, who is the inhabitant of the office, about his whereabouts. So it knows things like which meeting he's attending right now and what's next on his calendar and what's the probability that he's going to read email in the next 20 seconds. How about an hour? Is he in a different building of campus? Is he traveling at the moment? Tries to bring all this information together and provide a service to people who stop by the office when he's there and when he's not there and have an interaction with them about various tasks. So I'll show you a quick video.
Are you here for the 5 o'clock meeting with Eric?
No.
I'm sorry, I thought you were here for that meeting. Could you please swipe your badge? Eric is not here at the moment. Let me look at his calendar to see if I can tell where he is. His calendar says he should be at a meeting in his office now, so I'm actually not sure where he is. He will probably be back in around 15 minutes or so. Would you like to leave him a note, or maybe come back later?
We'll come back later.
Okay, you could try sending him an email message. I expect him to look at his email in around 10 minutes. Guess I'll see you later then. Bye-bye.
Thank you.
Hi Eric. 2 people stopped by to see you. I said you'd be back in around 15 minutes.
Great.
Catch you later. Bye-bye.
Thanks.
I'm sorry that some of the audio levels are a bit messed up in our videos, but here's another example. This is the robot that Cha was mentioning before. So we have one of these little guys on each floor as you come out of the elevator, and they can give directions. They have an electronic map, basically, of the building. They can give directions to people's offices, to conference rooms, to cafeterias, and so on.
What room number are you looking for?
Conference room 3800.
To get to conference room 3800, go to the end of this hallway. Turn right and go straight down the hallway for a bit. Conference room 3800 will be the first room on your right.
Thank you.
You're welcome.
Also, where can I find John Doe?
John Doe is in office number 4120. To get there, take the elevator up to the 4th floor. Turn right when you exit the elevator and continue to the end of this hallway. John's office will be in that wing of the building.
Thanks.
Okay, so hopefully this gives you a sense of the kind of systems I'm talking about and what I mean when I say physically situated dialogue. So what I want to do throughout the rest of the talk is give you a sense of what are some of the challenges in building these systems and what are some of the problems with language in these kinds of settings. So if you start at what people do when they come together to interact with each other with natural language, if you look carefully at it, we actually coordinate actions with each other in parallel without thinking much about it to accomplish a bunch of goals. We're pursuing a number of different goals in parallel. First of all, we have to solve a channel problem. We have to make sure that I know that I'm engaged in a conversation with you, and you know that you're engaged in a conversation with me. We have to open this communication channel, we have to maintain it, and we have to break it whenever we feel like breaking it. And that takes actually a lot of work. There's a lot of nonverbal behaviors involved in how I approach you, how I position my shoulders, where does my gaze go, and so on, that coordinates all this. We don't pay attention, we're very good at it, we just know how to do it, but once you start looking at it and try to get machines to do it, it gets complicated pretty fast. So there's this first level problem of engagement. How do we manage engagement? Once you can solve this problem and maintain an open communication channel, we need to pass signals to each other, and that needs to be coordinated. If you think, for instance, of the linguistic channel of language, we tend to take turns in conversations. We actually overlap much more than we think we do, but there's a certain structure in there. We don't all speak at the same time. It wouldn't work. So there's a lot of coordination that happens just in passing these signals, and only once you're kind of able to do that level of coordination, you start worrying about understanding what's behind these signals, what's the meaning behind them. So only in this kind of third layer you start to get to problems like speech recognition and language understanding and decoding what is it actually that these signals contain. And then, of course, as you go even higher level, you have to worry about the meaning of these things in the longer term context, in how we form our plans and our interactions for the long run. So you have to do a bunch of planning and sort of long-term thinking. And you can think of this almost as a minimal stack of communicative competencies. And I say minimal, and I really mean it because there's much more going on. But these are some basic things that you need to have into place in order to do language interaction in physical settings. And so my research agenda over the last years has been basically looking at this and trying to build models for these various communicative competencies by reasoning deeply about the surrounding context, about what is going on around, the who, the what, and the why of the surroundings. So this is kind of the one slide that has driven me in the last 5, 6 years and some of the work that you see. We're trying to now look bit by bit at these different models and try to build them up and try to get them robust enough so that systems can interact with language in this kind of physical settings. And so what I'm going to do in the rest of the talk today is I'm going to take 2 example problems. Over the years, we've done a bunch of work, and I'm happy to talk more offline with you guys about any of the other bits we've worked on. But I'm going to focus today just on showing you something about engagement and something about turn-taking, just to give you a flavor of the nature of the problems, the techniques that we generally use, some of the challenges that arise. And then, like I said at the end, if I have time, I'll make some broader comments about sort of things we've observed over time as being challenges with developing these systems. Does that make sense? Cool. Any questions so far? No. Okay. So engagement. Well, engagement, as I said, is this process by which people initiate, maintain, and break the interactions that they have with each other. And there's a wide body of literature in sociolinguistics and psycholinguistics. People have looked at how this works in human-human settings, starting with the 60s. And they show that there's many nonverbal signals that essentially matter. Spatial trajectory matters, proxemics, how close I am to you and how I position myself matters. Gaze matters, attention, hand gestures. All of these things come together to regulate this process of, think next time you're at a party out there and you insert yourself in a group of like 3 people that are already having a conversation. There's a law that goes on with the bodies of everyone and with gaze, that regulates how all that happens. Now, if you look in contrast what we do in current speech interactive systems, traditional solutions are very simple, and that's good because they work, and that's all we need. So if I have a mobile phone, a push-to-talk button is all I need to do engagement. I push this button, and the machine knows that I'm engaged with it. But that works fine because I'm holding it in my hand and because attention is assumed to be one-on-one, fully always here. If this is a robot going around the room and kids are around and the dog is around and everything is kind of how it is in the world, buttons are not going to work that well. And so in some of the research that we've done, we've looked at how do we create computational models for this process that enable machines to do engagement in a more natural way in physical settings. And so the types of models that at the representation level, what we want to be able to model is I have a system, and there's people that are potential interactants in the surroundings, and they come and go. They're not stationary. And some of them fall outside the field of view of my sensing, of my cameras, of my microphones. But what I want to be able to do is I want to be able to track engagements. Engagements can be multi-party. So here by this rectangle, I denote like an engagement, an active engagement between the system and 2 people. So I want to be able to track who's engaged with whom. And there might be multiple such engagements going on. The system, for instance, might have suspended temporarily an engagement with someone just to go do something with someone else for a while. But it needs to keep track that, hey, that was an engagement that was there and was suspended. And ideally, in order to really manage this problem, you want to think about engagements between others so that you know when you bring yourself in there, how to do it. And so that's the kind of representation we're trying to construct and working with. And now, once you have a representation, there's kind of, the way I think of it is there's kind of 3 classes of problems you have to solve. You have to solve an inference problem. You have to make sense of the world. So you have all these sensors like cameras, microphones, and you need to be able to track the engagement state, actions, and intentions of people around you. Once you can do that, then you need to be able to make decisions. If I know that you want to engage with me, well, should I engage with you or not, or maybe when? And these decisions need to be made in real time, right? You can't wait too long because time matters. And then finally, once you've made a decision, like, hey, I want to switch from being engaged here to being engaged there, you need to be able to render it to produce the right set of behaviors depending on the affordances that you have. So if you're a robot that can move around, you have to move. If you're just an avatar, you can turn ahead. If you're a circle, you can beep. I don't know, whatever the affordances are, you need to somehow signal that so that everyone around understands what your state is and what you're trying to do. And so there's these three classes of problems, and over the years we've done work in these various layers and various problems here. What I want to do is start by showing you an example video. This is a demo video, so it's shot in the lab. This is one of these things. So one thing I want to say is you'll see a bunch of videos, and I want to make it very clear. It's easy to shot a demo video that looks cool and works. This stuff is harder to do in the real world when you actually deploy it out there. But I want to start by showing you a demo video that kind of illustrates the flexibility and the kinds of behaviors that a system might be able to have once you have this kind of representation in place and the right building blocks. And then it becomes a question of, can I get these building blocks to be robust enough? And so the video you're about to see, so it's going to show you the systems view of the world. And this is from a system we developed early on that was booking shuttles on campus, right? So Microsoft campus is big. You can go to the receptionist and say, hey, I need a shuttle to this other building. We were trying to do this with one of these virtual avatars. It's one of these floating heads like the one you saw in the video before. You're not going to see the system. You're just going to see the system's view of the world. And a couple of things I'll say before I play the video. So you'll notice, of course, it does tracking. The red dot that you'll see glancing around shows the direction of the avatar's head. So as the avatar is interacting with different people, is looking at them. And engagements are denoted by these yellow lines below the faces. So this yellow line down at this point says that the system is actually in an active engagement with Eric, and this engagement with me is suspended. This line is dotted here. You'll see that the system is able to track head orientation and attention. It kind of brings all of this together to construct an interaction that's pretty fluid if you look from the lens of engagement.
Hi. My name is Laura, and today I'm here to help the receptionist with shuttle reservations. What's your name?
Dan Bohush?
Are the two of you together?
No.
Okay. Let me start with you first. Do you need a shuttle?
Yes.
Which building are you going to?
Building 34?
And this is just for you, right?
Right.
I'm making a shuttle reservation for you for building 34. Let me know if you need anything else. I'll be with you in just a moment. Excuse me. You will be on shuttle 56. It should be here in 2 minutes.
All right, thank you.
Bye-bye.
Bye.
Now, let's see. Do you need a shuttle?
Yes.
Which building are you going to?
Building 9.
And this is just for you, right?
Yes.
I'm making a shuttle reservation for you for building 9. Let me know if you need anything else.
Thanks.
Let's see. I should get the shuttle number for you in a moment. You will be on shuttle 68. It should be here any second.
Thank you.
Bye-bye. Let me check on your shuttle. You're still on shuttle 56. It should be here in 1 minute or so.
All right, great. Thanks a lot.
Bye-bye.
Bye.
So there's a number of things that go by pretty fast there, but it's an interleave of different kinds of models, that all contribute to creating this end-to-end interaction. At the moment, at some point where the system turns back and tries to re-engage with me, my attention is somewhere in my cell phone. The system understands that, and even though it knows from the decision model that, oh, my decision is to engage with this person, the way it chooses to render it is different than how it would if my attention wasn't in my cell phone, right? Because my attention is in my cell phone, first it says, excuse me, and waits for my attention to go up before it actually continues the interaction, right? So there's each of these different models, they're layered, and their blending can lead to that kind of end-to-end interaction. The question is, can we get this to be robust out there in the world? Can it really work that way? I mean, that's an actual real system. It's just that, speech recognition errors are high, vision doesn't work that well all the time. There's all these issues with perception and robustness. And so over the years, we work on increasing robustness in these various kinds of models. And I want to now do a little bit of a technical dive into one problem to give you an example problem and concrete problem how we go about attacking one of these problems. And the problem in this case has to do with the process of disengagement, how we manage, how do we know when we terminate an interaction. And to motivate this problem, I am going to show you another video. This is a random, unscripted, these robots are deployed in the building, random people go by and interact with them. So this is a completely uncontrolled interaction that someone had with the robot. Pay attention to how the robot actually doesn't know when to properly disengage.
Do you need help finding something?
Where's the restroom?
The bathroom is just down that hallway and on your right. By the way, would you mind swiping your badge on the reader below so I know who I've been talking with? Got it? Thanks, Luis. Is there anything else I can help you find?
No, thank you.
Sorry. Say that again?
No, thank you.
I'm sorry. I still didn't get that. Can I help you find something else?
No, thank you.
Okay then. Goodbye.
Yeah. And he's trying to find the bathroom, so not a good time. So obviously the robot does a kind of a terrible job here in terms of sort of breaking the interaction at the right moment. So what is actually going on? Well, for all of us humans, the moment we see that, we know that guy is leaving, right? Now the robot has a Kinect, but we're using it just for speech recognition for the microphone array because the field of view is too narrow to support this sort of multi-party group of 4 people around me interaction. And so a lot of the vision analysis we're doing is from RGB cameras. We don't detect this gesture at this point, you know, and even if we did, not everyone says bye. You could do a little bit by tracking their shoulders. People's shoulders tend to turn before they're about to actually go. In any case, our current robot has no idea at this point T0 that this guy is leaving. For as much as the robot is concerned, there's a big square face right there. And because of that, the robot launches this next dialogue contribution that's fairly long. Is there anything else I can help you find? And this is a long utterance, and by the time we get towards the end of it, it kind of becomes clear to the robot perhaps. Now we can kind of tell, even the robot can kind of tell that, okay, maybe this guy is on his way out. But by that time, it's too late. We've launched that utterance already, and when the guy hears it, he already stops and comes back. And so the key idea here is that if we were able to somehow learn to forecast, to anticipate that this person is going to leave in T0 plus alpha, then we could mitigate this situation by using hesitations. This is something people do all the time. In situations of uncertainty, we hesitate. Instead of launching into a thing, I could just launch one of these fillers like so. And then if at T plus alpha I figure out that you're actually going away, I can say, so, well, I guess I'll catch you later. Or alternatively, if I figure out, no, you're still around, I could say, so, is there anything else I can help you find? Right? So essentially that filler buys me time to really figure out what is going on and create a more smooth interaction. So that's the idea, and people use fillers and hesitations all the time to mitigate these kinds of uncertainties. Now, how do we actually build this? The system has access to a lot of multimodal streaming information, right? We're doing vision, we're tracking. I have here just some of the streams illustrated, like there's for instance, the location of the face in the X dimension, right? So you can kind of tell that the guy is stationary and then at some point he starts drifting away. This is the size of the face, which is some sort of measure of proximity, how close or far they are. And again, you can tell they're leaving. This is an output of a probabilistic model that the system uses to track attention that says what's the probability that the person is attending to the robot or attending somewhere else. So you can see the pattern in there. So we have all these streams, and there's many more of these. And the key idea here that's interesting with forecasting is that the system can actually learn by observing what happens in the interaction and just rolling back time. So, in machine learning, oftentimes you need to label data. Here, the system kind of does the labeling by itself. You just kind of watch what happens, and then you roll back time. So let me explain that. Suppose you start with a heuristic for predicting when people are disengaging. That's very conservative. So, you're just relying, let's say, on the size of the face. When the face is really small and far away, I know for sure you're disengaged. Now, it might be too late by then. If I only know then, it's too late. I want to know earlier. But hey, I can construct this thing that has very low false positives, right? So this will tell me at some point with high probability, yes, I'm sure they're done. And then what I can do is I can take this heuristic that the system has and roll it back in time. So essentially I want to say, hey, I want to anticipate that this will jump up there in the next 5 seconds. So I can construct a label automatically. That's 1. I want to predict 1 in this entire region. And I want to predict 0 otherwise. In essence, I'm rolling back time. The system observes what happens and then tries to anticipate its own sensors by about 5 seconds, right? So I generate labeled data automatically, and then I just train the machine learning model, and I use a lot of these features, towards those labels to make this prediction. And so now, there's a trade-off here that happens between how early I make the detection, So suppose I train the model and suppose the model gives me these predictions, like it looks like that, right? It's a bit earlier than this guy. It's not 5 seconds earlier, but it's a bit earlier. So if I use the same threshold, of confidence, then this is how much time I gain. I'll call that the early detection time. Now, as I move this threshold up and down, I can make the detection earlier and earlier and earlier, but I run a risk of these false detections, right? If I move the threshold too low, I'm going to detect this as being a disengagement when it's actually not. So I can sort of increase how early I'm going to detect, but I do that at the risk of sort of increasing also my errors. So here, for instance, I have a plot that shows you in a baseline. The baseline is the red line. What the heuristic does is the trade-off between this error, false positive rate, and how early, on average, I detect. And so you can see that, like if I want to detect about 1 second early, like with a heuristic, I'll have about 8% error. But if I train one of these machine learned models, I can reduce that error significantly. Or the other way to look at this is to say, hey, at the same error, I can increase how early I make the detection by that much when I go from my original heuristics to these machine learned models, right? So that's an example of using sort of machine learning in a multimodal way with leveraging features from different places. And one interesting aspect here is that multimodality tends to help in this system. So, here's, I guess what I have here is classification error and mean squared error. There's a majority baseline, there's a heuristic model. And if you look at, these are trained machine learned models trained using only certain kinds of features, like focus of attention features or phase location features, dialogue features. None of them actually do even as well as this heuristic that I manually authored myself. But once you start putting them together, you get better and better performance, and you beat that heuristic. So generally, adding multiple features, multiple knowledge sources in these systems helps. So this is an example problem, that we work on, try to build the robustness in how this robot does disengagement. Now, of course, this is just the inference, the sensing part. I still have to now make decisions and decide when do I put those hesitations in and so on. And that's a whole other, question. I'm not going to go into that in detail. But I wanted to give you a flavor of the type of work and how machine learning plays a role in sort of getting this robustness and enabling systems to interact better. Couple of observations sort of based on this work. Timing of actions is important in these systems. These are observations that are more general than this particular study. These are observations that we've noticed over the years, and we keep coming back to them. Timing matters. A lot of times in these interactive systems, you have these act versus wait trade-offs. This was one example where, I can act now or I can wait a little bit and get more information, but by the time I have more information, it might be too late. So decision-making under sort of time pressure is an important problem in these interactive systems. Another sort of important bit is that the ability to forecast helps as is important. I think we as people do forecasting all the time. We can finish each other's sentences, I think, on faster paces that all the signals have time to travel through our cortex and everything. Like, we are so good at and so fluid in how we interact with each other that I think it has to be that we're actively predicting what is going on. And what's interesting is that in interactive systems, you have these kind of opportunities like the one I just described, where you can learn from interaction. Like you can get your data labeled in the interaction because the system will eventually observe. It might go wrong, but it will observe that it has gone wrong probably. And then you can roll that information back. You can create these feedback loops, and roll that information back and leverage it. And that, essentially, most forecasting problems are of that nature. And then the third point I think that I wanted to make sort of as a high-level sort of take-home message is that this idea of multimodal fusion of leveraging multiple knowledge sources can often bring improvements in conjunction with machine learning models. So these are some of the things we've observed over time in this work. Unless you guys have questions, I'm going to switch gears and talk about turn-taking a bit. Yes? Yeah, so the question, I'll repeat it. You mentioned that, in the interactions that I show, people are quite polite and well-behaved. And that's true. In these videos, they are, but they generally are not. You're absolutely right. We've actually done studies, and I think that's why I like to put the systems out there in the world, because we've done studies, for instance, with turn-taking, where we bring people in the lab, multi-party, let's play this questions game with a system with 3 people in a system. And everyone is so nice and stiff and sits right there where you put them, and they talk to the system, and they take their turns. When you go out there in the world and you have this thing in front of the elevator, there's oftentimes groups of people. People talk to each other. They'll be like, Joe, where are my keys? Oh, you dropped them there. Then they come back here and expect that this interaction will continue at the right moment. So we see a lot of these sort of very naturalistic kind of behaviors, and you're absolutely right. There's a large variance in sort of people's attitudes towards this technology. I've seen people that are very sort of, how do I put it, like restrained, very, very sort of, when they go and, and there are people that are sort of all over, and, there's a large amount of variance, and if we want these systems to really be there in the world, we have to solve those problems. We have to get perception to be robust enough and work in those conditions. Yeah, it's a problem. Anything else before we switch gears? Yes. Yeah, she's bringing the microphone.
You mentioned multi-sensor fusion. What type of sensors you think we should look at it?
So in the work we've done, at least, it's a lot of vision, speech, and higher levels of understanding of the interaction, like dialogue and interaction state kind of information. In a vision sense, there's layers, perceptual models, right? Like we start at the pixels, we do various kinds of tracking, but then there's machine learned models that, for instance, track visual attention. I can track geometric attention, like where's the 3D angle of your head, or I can track attention towards targets in the scene. I know there's these 3 targets, and is it there, there, or there? So there's a variety of signals. A lot of them are visual. There's some speech information about the structure of the interaction. How many seconds since you last spoke, and who is it that last spoke, and who do I anticipate will speak next? What's the dialogue state? Did I ask this question? Is this the 3rd time I'm asking this question, and so on.
So you're not assuming that you could use, for example, some sensors in the cell phone of the person?
Well, maybe tomorrow all these sensors will be in the cell phone for all I know, right? Like the sensing that we're doing is basically high-resolution RGB cameras and microphone arrays. So a lot of, that's at the base. There's nothing more fancy than that at the base. We're not even using depth right now, right? But of course you could do that. So I don't put it past. There's questions about processing power and how much you can lift, but I think these things are getting better and better every day. So I wouldn't be surprised to see that kind of technology in phones in a few years. Yeah. Okay, I'll take one more and then I'll keep going and then we can come back at the end. Yes. Oh, maybe she's...
Hi. I wonder if you can clarify what do you mean by learning by interaction, like labeling data by interaction. It sounds to me like online reinforcement learning, but seems to be a little bit inefficient, like to learn in that way. I don't know.
If you have other sources of, if you can learn in different ways, I'm not arguing, I'm not saying it's a very efficient way to learn, right? Especially with a single, so this is similar in some sense to various kind of reinforcement learning approaches. What I'm doing here is I'm doing just supervised learning, in essence, propagating a label back in time. So it's a very simplified version, right? I'm not doing a temporal credit assignment problem. I'm not trying to solve a chain of actions. I'm just trying to anticipate a particular event that will happen in the future, and because the system will see the event in the future, I can do it. You're right, I don't think it's necessarily the most efficient way to learn. There's trade-offs, there's advantages and disadvantages. For instance, one of the advantages is that it is a way to learn in situ. Like you learn exactly what's specific to your situation and where you are, right? So we did experiments with one of these systems where we made it learn something about engagement. We learned the model, we got enough data to train the model, and it learned how people initiate engagement. Try to predict, is this person going by or are they going to come talk to me, right? Then we turned the system 90 degrees. Well, that model was no good anymore. That's kind of depressing, it's not so good. Now the question is, how much data do I need to see and where do I get the data so I can build a model that's really generalized? That's tough. But if I have a method that learns online in situ, that when I put it there, it just starts learning in that particular situation, then at least I'm adaptive. I'm not saying it's the better way, it's just trade-offs, right? You kind of have to pick your battles, I think. I'll keep going and we can have more questions at the end. So turn-taking. Turn-taking, in my mind, one level up from engagement. So let's say we've solved the channel problem. How do we pass signals and how do we coordinate with each other on these signals? Well, just like engagement, this is a very sort of rich, mixed initiative, locally managed, very coordinated process between people that involves a lot of verbal and non-verbal signals. Now, in current speech interfaces, a lot of them are still aimed, a lot of our computation today is aimed towards this dyadic one-on-one setting, where it's me and the machine, and it's me to the machine, and my attention has to be fully here, and you cannot go there for a second, right? When you're thinking about physically situated system and you have to deal with a real world, with multiple participants, the problem gets complicated. So traditional solutions are, again, this push-to-talk, or in a lot of dialogue systems, there's these simple turn-taking approaches that kind of make the assumption that you speak, then I speak, then you speak, then I speak, and it's this kind of volley, and maybe we allow some barging. All of that clearly breaks the moment you have three people interacting, because if you speak, I don't know if I'm supposed to speak or he's supposed to speak and which way we should go. And so in some of the work we've done, we've overlaid on top of the engagement model I've shown you before, we've overlaid a turn-taking model, where at the representational layer, the idea is that we're modeling who has the conversational floor, who is the ratified speaker that we all agree should be speaking at this time. So we're trying to track who has that floor. We're trying to understand who's talking, who are they talking to? Is this person saying that to them or to me or to both of us? And then how does the floor transition from one person to another? So we're trying to do all of that, again, from sensors with various kind of inference models. And then based on that, we're trying to act and speak at the right time. And so just like with engagement, there's an inference problem. We have to sense who's talking, who are they talking to, and what are the various floor control actions. When is someone trying to release the floor, and who are they releasing the floor towards? And you can use signals like attention and how long was the utterance and all that stuff. And then, so for instance, this is a capture from the, trivia game that we had that would engage with multiple people talking. And so at this point, the system understands that she's the one having the floor, she's the one talking, that's this little, speaker sign there, but she's talking just to the two of them, not to the system at this point. And then we understand that at the next point, she's actually pushing, releasing the floor towards these two participants, but not towards the system. And we do that based on where her attention is and the fact that she said a really long utterance that was ungrammatical, so it probably, well, ungrammatical as long as the system was concerned, probably not addressed to the system. But based on that understanding, the system, for instance, can now shift gaze to her, because it knows she talked to her. So the system, before this person starts talking, already shifts gaze to her, and then she starts talking, which creates for the whole fluidity in these interactions. So those are the kinds of problems that you're trying to do by, again, using this kind of multimodal fusion machine learned models from all the lower level signals that you have from vision and speech. Then you have to make decisions, and here real time really matters, like 200-300 milliseconds starts mattering when you do turn taking. And then you have to, again, render these decisions into an appropriate set of coordinated behaviors. And coordination is, again, key word here. And so I'm going to do another one of these small dives into one particular project just to give you a sense of, the types of coordination, that comes into play. This is inspired, actually, by a work by Chuck Goodwin. He's at UCLA. He wrote this book, I think, in the 80s, Conducting Interaction. It's fascinating. I'll show you a few examples from his book. So everyone that does speech recognition knows that speech, if you take conversational speech, is quite disfluent. If you transcribe, literally what people say in conversations, there's all these hesitations and false starts and, restarts. So it will look like this. Anyway, I went to bed. Or, Brian, your kids will have to go. I come in, I no sooner sit down on the couch. So it's all full of these disfluencies, and these are sort of, they're tough for speech and recognition and so on. Goodwin's insight was to look at conversational speech with all these disfluencies in conjunction with gaze. So if you look now at the gaze of the listener, that's the pattern we see, where the red portion is the portion where the listener is not looking at the speaker. This is the point where mutual gaze gets reestablished, and from here on, they have mutual gaze. So that's kind of interesting. So Goodwin had this anecdotal observation that, there's actually much more grammaticality when you look in regions of mutual gaze in human conversations. So that brings up this conjecture that maybe these disfluencies that we have, they're not all errors in production. They're not all some sort of something goes wrong or I'm not finding my words. Maybe some of them have to do with coordination and with regulating the interlocutor's attention. Like if I start talking and you're looking away or you're distracted, maybe I'm going to put some stutters in. And all of this happens unself-consciously, like it just happens, until your attention comes back so I can deliver the entire message to you. And so, so this is Goodwin's work, in socio-psycholinguistics. Here's now what the robot does. Here's how good the robot is at dealing with people that have attention somewhere else. This is Sue trying to get to a conference room.
Do you need directions? Sorry, say that again?
I'm looking for my meeting.
You said Matt McGinley, right?
No, give me a minute.
Sorry, that was Alberto Bacalli you wanted, correct?
That's really wrong. Bye.
Well, guess I'll see you later.
Not good, not good. So, you know, we're tracking visual attention, and we're using it for engagement and all these other things, but we're not using it for turn-taking. We're not using it, you know, we don't realize that, hey, her attention is in her cell phone. She's trying to figure out where the meeting room is. The robot keeps yapping and yapping, you know, doesn't pay attention to that, to do turn-taking. So I said, hey, there's this interesting Goodwin work. Why don't we try to make our robot stutter? Let's see what happens, right? What we do is we build this attention coordination model where now, on one hand, we have attentional demands. So there's a model inside the robot that says, every time I produce an utterance to someone, I expect their attention to be in certain places. Now, I don't expect always, this depends on the dialogue state and what utterance I produce. I don't always expect attention to be on me, the robot. If I point there to the end of the corridor and say that, you know, I expect that your attention will go to where I point, but then it's going to come back. So the robot, anyhow, we endowed it with this model that tells it where it thinks the attention should be. And then we measure where the attention actually is for that participant by, again, using these visual models of head orientation and so on. And whenever there's a mismatch, instead of just like training through the whole thing, we actually try to coordinate with a person's attention. So we have this coordinative policy that, in essence, will do some of these stutters and hesitations. Like, you know, if the attention is not where it should be at the beginning of the phrase, the robot will just hesitate for a bit, we'll just pause for a bit. Then we'll try to attract attention with an interjection. Then he might pause some more. Then he might launch the phrase, but not the entire phrase. He might launch just the first two words. In case the attention is still not there, he might still wait some more, right? So we kind of try to do the same kinds of things that humans are doing, you know, when attention is not there, and coordinate more with a person's attention and try to get their attentions back. So that's the idea. I want to, again, show you a demo video that illustrates how it works in the good conditions, then show you a bunch of actually naturalistic videos, see what happens out there when we deploy it in the world, good and bad. So here's the demo video.
Do you need help finding something?
Yes.
Could you tell me the room number or person you're looking for?
I think it's 4800.
To get to 4800.
No, I think it's 4300. 4300, yeah.
Excuse me.
4300.
Go along that hallway.
I'm looking for 4300.
4300 is just down that hallway and will be the first room on your left.
Okay.
By the way, would you mind swiping your badge on the reader below so I know who I've been talking with?
All right, so now here's the robot view of the world. So what is going on here, the robot is trying to produce this phrase that I think says to go to 3800 or something like that. And normally we just say it, but this is the inference about where my attention is going. When it's high, it means my attention is on the robot, then it goes away from the robot. And because it's away, in all these points, the robot introduces all these hesitations and, you know, interjections and stutters until basically my attention comes back. So this video is going to have some sidebar comments to illustrate all that.
It's 4800.
To get to 4800. Excuse me. Go along that hallway.
I'm looking for 4300.
4300 is just down that hallway and will be the first room on your
So anyhow, hopefully this gives you a little bit of a sense of the internals and the robot's view of the world as it's trying to do this coordination. Now here's some real world examples. This is again completely unscripted, random people going by interacting with the system. What you see at the top is, the phrase that the robot is producing, and it's split into sub-phrase units, right, as the robot is saying these things. And the stuff in black is the stuff that the robot is planning to say from the very beginning. The stuff in orange is injected on the fly dynamically by the robot as it figures out that the attention is not quite right.
Take the elevator down to the second floor. Turn left as you walk out of the elevator and continue on to the end of that hallway. Excuse me. 2800 will be on that side of the building. Huh? Excuse me. Can I help you find something?
Can you tell me?
Morning. Do you need directions? Excuse me, do you need directions?
How to get to 222?
Kind of a pushy robot, but that's the job. So this is what happens when things work well. And actually, when things work well, and I've had this experience, you actually almost don't even realize it's doing that. It's not registering. It just seems normal, right? Of course, things more often than not don't go well. And so I don't want you to leave this room thinking like, oh my God, these guys have solved this. No, it's a very tough problem. Like I would say half the time, more than half the time, this stuff doesn't work as it should. And so I want to show you a few examples of failures. Here's a case where the robot incorrectly thinks that people are not paying attention when they actually are paying attention, and injects all these hesitations and interjections, and that makes for, it's not very, it's not very good. I guess one point I want to say here is a lot of the problems we have in this system still, coming back to the AI, are in perception. Like if perception was better, some of this coordination stuff that we're doing at the high level is not that tricky. It's a couple of heuristic rules. It's not that sophisticated. If I could really accurately track where the person's attention is, or maybe even anticipate that, that would be fantastic. We can create a lot of beautiful interactions. Anyhow, here's the example.
By the way, would one of you guys mind swiping your badge on the reader? Got it? Excuse me. Thanks, Annie.
She's like, what? And the robot just needed to say thanks, and for that said, excuse me. Weird. Here's another one. Here, the robot points, to somewhere. The participant sort of looks there. Then the robot waits for their attention to return. But because the robot has this wait period that's a bit longer maybe than what a human would do, and the robot's gaze is probably not in the right place, the person assumes that the robot is done talking and just leaves. So the robot doesn't even get a chance to give the directions. So it's interesting kind of errors that show up.
Chris J.C. Burgess's office is 3928. To get there, walk to the end of that hallway. Oops. Well, guess I'll see you later.
So the errors also happen in interesting, unexpected ways, right? It's like when you chain a bunch of these things together, it leads to sort of interesting results. But hopefully this gives you a sense of the kinds of problems we're dealing with. So I talked a bit about turn taking. I talked about engagement before. What I hope to have done is kind of give you a sense that there's much more to language interaction when we bring it in physical settings than just thinking audio and speech channel. There's a lot going on in the nonverbal channel with how people behave with each other. And so there's a lot of open territory there, I think, for study. If you guys have more questions, we're 10 minutes away. I can take a couple more questions now. I have a few more slides just with some high-level points about integrative AI and what building these systems means. But maybe I'll take one question and then we'll finish the rest of the talk.
We tend to gesticulate more than other people. And how do you see the insertion of this difference in the cultural and the gesture?
There are cultural differences, right, for sure, in how people sort of in their body language, and so we need to study those things, right? There are studies in human communication dynamics on those themes. One thing that I would say is that I wouldn't make one thing that has surprised me, I guess, if I think of where I was thinking, 5-6 years ago after seeing all this data and people interacting, there's a tremendous amount of variance even within a population. So even if you take, I guess building 99 at MSR is not, it's a bit strange people, I don't know. It's like, it's a certain population, it's not a very general demographic, but if you take that population, you will see a wide range of behaviors, even in the nonverbal and how they approach mentally, this interaction. There's people that think this is just a machine. There's people that treat it like it's a human. They wouldn't leave until the thing says bye. So there's, what I would say is I would caution about, I don't think we should expect variance. There's definitely variance cross-culturally, but you have to deal with a lot of variance just within one culture. I think it's even a big challenge. But for sure, there are all these differences, yeah. So I'll make one more. I'll take one more, and then I'll make some closing remarks. Yes?
The thing that you are, the kind of inference that you are solving remembers me belief tracking problem, right? You also mentioned belief tracking. For example, that variable that whether the person is paying attention or not is a random variable, right, that evolves from time.
Yep.
So belief tracking, you could solve belief tracking doing inference on a dynamic Bayesian network, right? Or maybe if you want to do approximate inference, you can do like a particle filter or something like that. So do you do that kind of stuff?
Yeah, so those kinds of models, so temporal tracking models, should be bread and butter in these systems. In a lot of these systems, and I'll come back to this in the last few slides, the systems are large, they're complex. And so usually when people do belief tracking or when they use a lot of machine learning technology is kind of built as this is the thing. There's one problem I'm trying to solve and I have one model for it. I don't think we can build one model that solves the entire language problem, so we need to compose a lot of models. And so there's a lot of interesting challenges when you take techniques like belief tracking and try to integrate them, for instance, in layered ways and so on. So because of those challenges, what we end up doing oftentimes in these systems is rely on simpler models actually than sort of this temporal inference model. So a lot of times we will do just frame by frame logistic regression maximum entropy inference models without temporality. We encode temporality into the features because we can compose, we can architect these systems and maintain them in better ways. But you're absolutely right, time and belief tracking kind of approaches should be bread and butter in these systems. Yeah. So let me make a few now. I'm going to switch gears completely. No more videos, and this is completely different for the last couple of minutes. Just some observations, I think, about just building end-to-end integrative systems, right? If you look at these systems, they have many different technologies in them. There's vision, there's speech, there's, and so over the years, we've come to the realization that platforms matter. And, the kinds of tools we have, the kinds of tools we build to enable ourselves to build these systems are just as important as all this other, research we're doing on language itself. And so I want to point out, I guess, a couple of different things that I believe are really interesting challenges if we think of AI and of this notion of integrative AI, and by that I mean how do we build systems that integrate many different AI technologies into an end-to-end kind of solution. So the first observation is exactly what I said before, that these systems are complex. They leverage many different kinds of components, and people will show you pretty architectural diagrams, but if you really go and look, it's a mess. It's all it's complicated. It's not easy. And so this is a listing, for instance, of some of the kinds of models that run into one of these systems, and it's all. So one thing that I think is important, and this is where it's kind of like the AI community calling for help to other computer science communities. Programming models for coordinated computation. All this stuff needs to run in parallel because we have all these real-time constraints. And so building these systems that are largely parallel, but where stuff is still coordinated, and the parallelism is not of a simple map-reduce kind of form, is interesting and challenging. And I feel friction with the kinds of tools we've had so far. So it's interesting for the people that are in that space to think about that and how, how we can do that better. We spend a lot of time building tools. I would say, like, I don't know if half my time is spent actually not building the systems, but building the tools that let me build the systems or understand how these systems actually work when they're integrated end to end. And so I think that's another area that is important. Another property of the systems, apart from their complexity, is that they act in real time and they act under uncertainty. When you have all these sensors, there's a lot of uncertainty. And so in my mind, there's almost like, I'm wondering if there's almost like a need to evolve our programming languages a little bit. For instance, time is not a first-order construct in any programming language I know of or I usually use. But time is something we deal with all the time. So, what I would like in a programming language is to have time as a first-order kind of citizen. Like, in C++ or in a programming language, I can say f is a double. I want to say f is a stream of doubles, and I want to compute with f as if f was a double, but I want automatic persistence and tracing. I want historical access. I want to be able to say, what was the slope of x in the last 2 seconds? And I want that to be built in and easy. Now, I can build all of that myself, and I think a lot of people that build these systems end up rebuilding those tools themselves. But there's this question somewhere deep, and I'm not a programming language person, but there's this question for me, do some of these things need to migrate lower in our stacks, in our systems, down into the programming languages or into the OS? Uncertainty is another one. We over and over, deal with uncertainty, so we build our representations of uncertainty. So again, just like I say double F, I want to be able to say uncertain double F and get representation sample and all these belief updates over X just happening, whereas I think just of X as a double, right? And go with that. Finally, a third point that I wanted to make has to do with this integration of, I don't know if this is the right way to think of them, but human and machine author components. So if I take this tapestry of components that is in one of these systems, a number of them, all of these guys, use machine learning in some way, and they're connected to each other. And so, like I said, a lot of times in the machine learning community, the questions that are being addressed is how do I get this technique to be better, or how do I solve this problem where this problem is an input to output kind of problem. Whereas here, I need to compose a number of these models. And from a software engineering standpoint, if I develop this system, I need to kind of have a sane way to maintain it and test it. And so what does that all mean? I don't know. I think there's interesting intersections between the machine learning community probably and the software engineering guys and understanding how do we build maintainable systems that compose this. And then finally, the idea of meta-reasoning and system self-level optimization. Like once you have this system that's composed of this sort of combination of components that are human-authored components generally have thin APIs, I would say, right? There's like a function call with 5 variables that I as a human can call. Machine learning component, like a neural net, can have very wide inputs and, they're a bit, I don't know, there's an impedance mismatch there. So there's an interesting question, I think, around software engineering and also around questions about optimization at the system level. How do I know that if I change something, I adapt this model and improve it a little bit, what is that going to do in the rest, deep down in the rest of my pipeline? How do I do joint optimization in these systems and so on? So I think there's really interesting questions sort of system level that people are starting to look at. And we've noticed this as we do work on this language problem. But my sense is that this happens in any kind of AI system where you're starting to agglomerate, to aggregate multiple kinds of technologies together because you want to build a certain end-to-end thing. So I'll stop there and I'll take more questions.
It's a great talk. We have maybe 3 minutes for some questions.
I think there's a question right there.
Thank you. My name is Carla. I work at Universidade Federal do Rio de Janeiro. Something that caught my attention is about the case where the robot keeps inserting these interjections and excuse me and this sort of stuff. And if I were in a situation where I would be looking for information and a machine would be there to give information to me, I would be bothered if I was looking at my mobile and the machine would keep up, asking back for the attention. So, come on, you're a machine. Why are you so anxious? Can't you wait? So I wonder if this is like I think your goal is to reproduce human behavior, but perhaps this anxiety could be left out or some other type of human behavior shouldn't be there all the times.
Yeah, no, I actually quite agree with you. So let me clarify a bit because I don't wanna misunderstand here. So I'll say two things. One is I think if you're there and looking in your phone and the robot keeps saying "excuse me," we've done a poor job, right? Like that's not what a human would do in the first place. But I don't think a human would keep prodding you and saying "excuse me, excuse me, excuse me." Maybe it would. But the higher level point actually renders the first point mute, I think, which is I think you're right. Like what I'm interested in is actually not reproducing human behavior. It looks that way kind of, but what I'm interested in is creating a zero impedance mismatch between humans and machines. That does not necessarily mean, and I think this is where I agree with you, that it's human-like behavior. The machines don't need to have human-like behaviors. But I would like to get to that point, like Rico said, where your grandkids will be like, what do you mean you had to learn how to use computers? Like, I want things to be zero impedance, to be completely fluid. For now, I'm using as inspiration what humans do, and I'm doing a poor job at that. But, you know, that's how I'm approaching it. But I actually agree with you. I think anthropomorphization is a very double-edged sword, and is not necessarily, like, it's not the answer. Like, you know, you have to have the right thing to, I think that's what I'm after, at least, to create this kind of zero impedance between the human and the machine.
One last question.
My question is about the platform and the last questions that you posed. I mean, it would be really interesting if I could test some pieces using the tools that you already developed. Are these tools available, or is there a planning to make them available, like really a platform that people could test dialogue systems?
Yeah, so they're not available right now. I'm hoping they will be available one day soon, but they're not available. Like right now, I cannot give you something. The code base is just like, you know, evolved over 6 years of, you know, craziness. But we are working on trying to create something that hopefully one day will be available for people, to enable people to build these kinds of systems and to study these kinds of problems, I think, yeah. I think tools is very important.
Is there a group worldwide interested in this kind of problem that we could talk about a common platform and people could plug their modules there?
So there's a couple of communities that kind of have had this problem for a while and have attempted to. So for instance, the robotics people, right? In robotics, this is often the case where, you know, everyone, like, it's kind of modular, and everyone hopes for this dream of modularity where your piece will come in and plug in nicely. And so there's a couple of, you know, infrastructures that exist, like ROS is the robot operating system. At the same time, I don't think they get to the problems I'm talking about, which is, you know, uncertainty and time and programming and all of these constructs. I don't know of, you know, of something that exists. I know in the machine learning community, for instance, there are incipient efforts. I've heard in the past year or so people starting to talk about integrative machine learning or systems level machine learning and how do you compose things, and those guys will have those problems. But yeah, I think it's very ripe for exploration and for doing work, I think. Yeah.
Thank you.
Okay, let's stand again.
Yes.